Welcome back to the Deep Dive. Today, we're jumping into the world of Richard Feynman, looking closely at sources like Lawrence Krauss's Quantum Man.
Yeah, and we really want to get past the popular image,
Yeah.
The bongo player, the fun personality.
Which does great stuff, don't get me wrong.
Oh, absolutely. But it sometimes hides the sheer, intellectual power and the unique way he actually did science. His nonconformity was key.
Totally. And I think the main thing to grab onto is that his genius wasn't just problem solving. It was finding a whole new way to think about the universe.
Exactly.
Okay, so let's dig in. Where do we start? His early life.
Makes sense. Queens, right. Very self-driven from the start. He wasn't just doing his homework. He was teaching himself advanced math.
Yeah, algebra, trig, calculus, stuff way beyond the high school level.
And crucially, he didn't just learn it. He had to sort of rebuild it in his own head, make it his own.
That's fascinating, those dactylo symbols he invented. Just because his typewriter didn't have the math keys he needed for this handbook he was making in, 1933?
Yeah. I mean, who does that? He's basically redesigning notation just to get his thoughts down properly. That tells you a lot about his mind right there.
And that independence really shaped his big decisions later, like at MIT.
Right. He started in math, but it didn't quite click for him. He kept asking, what's this for? What can it do with it?
And the answers weren't satisfying at all. Things like insurance calculations.
Or worse, the professor basically saying, if you have to ask, you don't belong here. A bit harsh.
Yeah, a little bit. So he found pure math kind of pointless, for him anyway.
But then engineering felt too constrained, too practical maybe.
So physics ended up being his Goldilocks choice. Just
Exactly. It had the theoretical beauty he liked, but it was always tied to, reality, to experiments.
And that really gets to the heart of his specific kind of genius, doesn't it?
I think so. He wasn't like Einstein pulling entirely new theories out of thin air necessarily. It was more about taking what was already there, Newton's laws, Lagrange's ideas, and finding a radically different, often more powerful way to look at them, always grounded in what actually happens.
That grounding seems vital. You mentioned his high school teacher, Mr. Bader, introducing him to big ideas like entropy.
Yeah, and the whole mystery of why time only seems to flow one way, past versus future, that really stuck with him.
And you can draw a line from that kind of thinking straight to his biggest contribution, right? The path integral.
Absolutely. It's amazing, actually. The roots go way back, like 300 years back, to Pierre de Fermat.
Fermat. Principle of least time. That's the one where light always takes the quickest path.
That's the one, 1662. And it always felt a bit weird, philosophically, like how does the light know in advance which path is fastest? Does it have some kind of purpose?
Okay, yeah, I see the problem.
And then later, Lagrange developed the classical idea of least action.
Right, showing Newton's laws could be framed differently, using that quantity kinetic minus potential energy that particles seem to minimize along their path.
But again, why just that one path? Why is nature so specific? That was the puzzle for centuries.
So Feynman comes along.
And, inspired by Dirac, he has this revolutionary idea for his PhD thesis. He takes that action principle into the quantum world.
And what was the leap?
He realized that quantum particles don't just take that single classical path of least action. They take every single possible path between point A and point B.
Wait, every path? Seriously? Like even ridiculously roundabout ones?
Every single one. Through all of space and time. It's wild.
So is that connected to something like the double slit experiment, where the electron seems to go through both slits?
Exactly. It's like the particle is exploring all possibilities simultaneously. The final probability of it getting from A to B is found by summing up contributions, these complex numbers called amplitudes, from all those infinite paths. That's the path integral.
Wow, okay. So for us living in the big, everyday world, why don't we see things taking all these crazy paths?
Well, that's the crucial part. For macroscopic objects like baseballs or us, the paths that are far away from that classical least action path, they interfere with each other destructively. They basically cancel each other out.
So only the paths really, really close to the classical one actually add up and contribute significantly.
Precisely. Which is why Newton's laws work so well for everyday stuff. Our classical reality is sort of the average result of all that underlying quantum exploration.
Okay, that makes sense. And this path integral approach, it wasn't just a neat idea, it was incredibly useful, right?
Right.
Especially in QED.
Oh, absolutely. quantum electrodynamics, the theory of light and matter interacting, was in a real crisis back then.
Because of the infinities. I remember reading about that. Like trying to calculate the energy of an electron interacting with itself just gave infinite answers.
Exactly. The calculations just blew up. It meant the theory was fundamentally broken, or at least incomplete. Feynman's path integral method, along with the diagrams he developed.
The famous Feynman diagrams.
Yeah, though Dyson helped systematize them. But the whole approach provided a clear graphical way to organize the calculations and, crucially, to handle those infinities.
Through renormalization.
That was the key technique, yeah. It involved kind of redefining the bare mass and charge of the electron with the values you actually measure in experiments.
So you sort of absorb the infinities into those measured values.
You could say that. It effectively swept the infinities under the rug, allowing physicists to calculate things like the magnetic moment of the electron to incredible precision, matching experiments perfectly.
But it sounds like a mathematical trick almost. Did Feynman see it that way?
Mm-hmm.
We'll get to that, but first, this whole experience taught him a really important lesson, didn't it? About theory versus reality.
Oh, definitely. He learned it the hard way, actually. There's a story about him and a colleague, Welton, trying to use an equation, the Klein-Gordon equation for relativistic electrons. Well, they rediscovered it, only to find out it was already known to be wrong for that purpose. Their calculations, as Feynman put it, in no way agreed with experimental results.
Ouch.
Yeah. He called it a terrible lesson, but a vital one. It hammered home that no matter how beautiful or elegant your theory is, it's useless if it doesn't match reality. You have to check it against the real thing.
That commitment to the real thing, to getting answers from the source, really showed up later in his life too, didn't it? Like with the Challenger investigation.
Absolutely. 1986, he famously hated committees, anything that took him away from physics.
But he joined that presidential commission.
He did. And his approach was pure Feynman. He didn't just read the official reports. He went and talked directly to the engineers, the technicians, the people who actually worked on the shuttle.
Asking those simple, direct questions.
Exactly. And then that incredibly famous moment on live TV.
The O-ring demonstration.
Yeah. Just taking a piece of the rubber O-ring, clamping it, putting it in ice water.
And showing everyone watching that it lost its elasticity, its ability to seal properly in the cold.
A brutally simple visual proof of the technical failure point on that cold launch morning. Just cut through all the bureaucracy.
Amazing. Switching gears a bit, but still on intense work, we have to mention Los Alamos, the Manhattan Project.
Right. World War II. His contribution there was immense. That lightning calculation ability people talked about was apparently legendary, essential for figuring out critical mass, the physics of the implosion bomb design, really complex stuff.
He even ran the computing group for a while, didn't he? Before the electronic computers were fully up and running.
That's right. Coordinating the teams of people, mostly women actually, who were doing the calculations by hand or with mechanical calculators. Huge, complex operations.
After the war, though, his interests started to shift, didn't they? He got a bit disillusioned with particle physics for a time.
Yeah, he felt the field was getting messy, maybe not enough clear progress, so he started looking for new problems, new areas to apply his thinking.
And landed on superfluid helium, the ultra-cold quantum world.
Exactly. Just a few degrees above absolute zero. It's this bizarre state of matter where liquid helium flows with zero viscosity, zero friction.
It can crawl up walls.
Creeps right up and over the edge of its container. It defies gravity, seemingly. He wanted to understand why.
And he used the path integral again.
He did. It was perfectly suited. He used it to show how the quantum nature of helium atoms explains this weird behavior. He also explained things called rotons, which are like little whirlpool excitations in the fluid.
And a key part of it was that helium atoms are bosons, right? What does that mean in this context?
That's crucial. Bosons are particles that, unlike electrons, can occupy the exact same quantum state simultaneously. Many bosons can pile into the lowest possible energy level.
Okay.
So in superfluid helium, near absolute zero, a large fraction of the atoms condense into this single lowest energy quantum state. They essentially act like one giant quantum wave.
And because they're all in the lowest state,
they can't easily lose energy by bumping into things or creating friction because there's no lower energy state for them to fall into. So they flow without resistance.
Wow, that's a beautiful explanation. His reach was just incredible. And it went beyond pure theory, too, like that famous 1959 talk.
There's plenty of room at the bottom. Yeah, visionary stuff.
He was basically predicting nanotechnology decades before anyone else was seriously talking about it.
Totally. He was speculating about manipulating individual atoms, storing vast amounts of information in tiny spaces. He did this calculation estimating you could write every book ever written on the head of a pin.
What was the number? Something like 100 terabytes?
Roughly, yeah. 10 to the 15 bits. This was way before Moore's law, remember? He saw the potential for miniaturization on a scale people just weren't conceiving of. It really set a target for the future.
And then, even later, in the 80s, he made another critical contribution, this time to computing itself.
Right. He showed mathematically that a classical computer like the ones we use every day fundamentally cannot efficiently simulate a complex quantum system.
Why not?
Because the complexity of a quantum system grows exponentially with the number of particles. A classical computer just gets overwhelmed. It doesn't have the resources.
So that work basically provided the theoretical justification, the need for developing something entirely new.
Exactly. It proved that if you want to simulate quantum mechanics properly, you need a quantum computer. That realization really kicked off the whole field we're seeing explode today.
So QED, nuclear physics, superfluids, nanotech, quantum computing. The breadth is just staggering.
It really is. But let's circle back to that Nobel Prize for QED, because there's a paradox there, isn't there?
Yeah, you mentioned his unease, even after winning the prize in '65.
He still expressed doubts about renormalization, the very technique that made the QED calculations work and won him the prize.
Why the doubt? It worked, didn't it? The predictions were incredibly accurate.
They were. But Feynman felt renormalization wasn't fundamental. He saw it as a mathematical trick, a stopgap. It hid the underlying problem of the infinities rather than truly solving why they occurred in the first place.
It just swept them under the rug, as he apparently said.
Pretty much. He'd hoped the path integral would lead to a more complete fundamental theory that didn't need renormalization. He felt he hadn't quite reached that ultimate goal.
It's incredible. Even at the peak of his recognition, he's focused on the deeper theoretical purity, the process, not just the prize.
He was always searching, never satisfied.
Cool.
Which leaves us with a really interesting question to think about.
Go on.
Well, what if the path integral formulation is the fundamental way nature actually works? Many physicists today lean towards that view that reality itself involves this summing over all histories. If that's true,
Then the very thing he won the Nobel for, but kind of dismissed as just a calculation tool.
might actually be the deepest insight, the biggest leap. It would mean his life's work, which he himself sometimes downplayed, could ironically be the most fundamental description of reality we have, a discovery perhaps even greater than he realized.